In 1980, a piece of equipment broke on a spacecraft that was already on its way out of our solar system. At the time, almost nobody thought much of it. It wasn't near any planet. It wasn't at any dramatic boundary. It just quietly failed, and the mission moved on. Except that one small failure ended up creating a 40-year blind spot in human knowledge, a gap in our understanding of the actual edge of our solar system that nobody could fill, until a completely different spacecraft, one most people have never heard of, reached that same boundary 6 years later and finished the job the first one couldn't. I'm not going to tell you which spacecraft broke yet, or which one saved the mission. Just sit with that for a second, because by the end of this video, you're going to understand exactly what that gap was, why it mattered so much, and why right now in the middle of 2026, NASA is about to attempt something on that second spacecraft that has never been tried before, at a distance where every single command takes over 16 hours just to arrive. Welcome to the space frontier. This is where we take the space stories that deserve way more attention than they get and break them down properly, with the real data, not the exaggerated version. And this is genuinely one of the best stories in the entire Voyager mission. So if you want more breakdowns like this, go ahead and hit subscribe now, because there's a lot more coming, and you're going to want to be here for it. Let's rewind to the beginning, because this story only makes sense once you understand there were always two spacecraft, not one. In the summer of 1977, NASA launched two nearly identical machines within about 2 weeks of each other, Voyager 1 and Voyager 2. Most people only know about Voyager 1, the one that crossed into interstellar space in 2012, the one with the golden record, the one that keeps making headlines. But Voyager 2 launched 16 days before its twin, and despite having the higher number, it was given a completely different job. Voyager 1 was put on the fast track, a trajectory built to swing past Jupiter and Saturn, and then angle sharply out of the solar system as quickly as possible. Voyager 2 was given something much harder. Engineers in the 1970s had realized that the outer planets were about to line up in a rare alignment that only happens once every 176 years. An alignment that would let a single spacecraft use the gravity of each planet to slingshot toward the next one in sequence. Voyager 2 was built to take advantage of that alignment fully, and it became the only spacecraft in human history to visit all 4 giant planets of our solar system. Jupiter, Saturn, Uranus, and Neptune, every single one of them, up close, in detail. Nearly 50 years later, no other spacecraft has ever repeated that. Here's the trade-off. Nobody talks about enough. Taking that longer, harder route cost Voyager 2 time. Voyager 1 crossed the boundary into interstellar space, a region called the heliopause, in August of 2012. Voyager 2 didn't cross that same boundary until November 5th, 2018, 6 full years later. For those 6 years, Voyager 1 had the interstellar spotlight entirely to itself, sending back data that was already confusing scientists and forcing them to question their models. But here's the twist, and this is the piece of the story almost nobody puts together properly. Voyager 1's data from that crossing was incomplete in a way that mattered enormously, because back in 1980, decades before it ever reached that boundary, the instrument on Voyager 1, specifically designed to directly measure the plasma around it, its temperature, its density, how fast it was moving, had already stopped working. That's the equipment failure I mentioned at the start of this video. It happened before Voyager 1 even reached Jupiter's orbit on its way out, over 3 decades before the interstellar crossing actually took place, which meant that when Voyager 1 finally crossed into interstellar space in 2012, the single instrument best suited to tell scientists what that environment actually felt like from the inside had already been dead for 32 years. Scientists had to work around that gap using other instruments, cosmic ray detectors, magnetometers, indirect measurements that could hint at what was happening but never confirm it directly. It's the difference between hearing a storm through a wall versus actually standing outside in it. And that gap sat there, unresolved, for 6 full years until Voyager 2 reached the same boundary in November 2018, carrying a plasma instrument that was still fully alive and working. That single working instrument is what makes Voyager 2's crossing one of the most important data collection events in the history of planetary science, and almost nobody talks about it the way they talk about Voyager 1. If you're enjoying this so far, this is a great point to subscribe, because we're about to get into exactly what that instrument found. And some of it genuinely stumped the scientists studying it. In November of 2019, 5 separate research papers were published simultaneously in the journal Nature Astronomy, describing what Voyager 2's plasma instrument had actually measured at the heliopause. And what came back didn't just add detail to what Voyager 1 had found years earlier. In some ways, it complicated it. The first big surprise had to do with where exactly the boundary sits. Scientists had always assumed the size of the heliosphere, the massive bubble our sun creates around the solar system, should expand and contract with the sun's own activity cycle, growing larger when the sun is more active and shrinking when it's quieter. Voyager 1 crossed the boundary during a period of high solar activity. Voyager 2 crossed it years later during a period of low solar activity. If the models were right, those two crossings should have happened at noticeably different distances from the Sun. Instead, both spacecraft crossed at almost exactly the same distance, within about 2.5 astronomical units of each other, a tiny difference on a scale where each unit represents the distance from the Earth to the Sun. Stimatios Krimigas, one of the lead scientists on the mission, put it about as plainly as a scientist ever does in public. He said flatly that they simply do not understand why. Think about what that actually means. This is someone who has spent decades studying this exact spacecraft, admitting on the record that a basic assumption about how our own solar system responds to our own sun turned out to be wrong, and nobody currently has a clean explanation for it. Then came the second surprise, this time about temperature and density. Voyager 2's still-functioning plasma instrument gave scientists their first ever direct measurement of the temperature of interstellar plasma, the material that fills the space between stars. It came back reading somewhere between 30 and 50,000 degrees Kelvin, hot by any everyday standard, but far cooler than the plasma just inside the boundary, which runs into the tens of millions of degrees. Combined with Voyager 1's data from years earlier, scientists could finally confirm something for certain. The plasma out in interstellar space is more than 40 times denser than the solar wind at the edge of our solar system. Space between the stars is not some empty, thin nothing. It is thick with material, colder than what's inside our bubble, but far more substantial than anyone had confidently measured before this exact spacecraft got there. But the discovery that the mission's own project scientist, Ed Stone, called the most remarkable of all was about the boundary itself. It leaks, not metaphorically, literally. Scientists had assumed the heliopause worked something like a clean wall, solar wind on one side, interstellar space on the other, a defined edge between the two. What both spacecraft found, approaching from different directions, years apart, was something closer to a coastline than a wall, with material genuinely crossing back and forth in both directions. Voyager 1 detected tendrils of interstellar particles pushing inward through the boundary before it even fully crossed. Voyager 2, approaching from a different angle, detected a trickle of solar particles leaking outward into interstellar space before it crossed 2. Two different mechanisms, on two different sides of the solar system, both pointing to the same underlying truth. Ed Stone summed it up by saying, "The Voyager probes are showing us how our sun interacts with the material that fills most of the space between stars in our galaxy." Notice the word he chose. Interacts, not ends, not separates. Interacts. That's not a clean edge between two worlds. That's a constant, messy, ongoing relationship between our entire solar system and the galaxy surrounding it, something no model had fully predicted before these two spacecraft went and checked for themselves. Now step back for a second and actually think about what Voyager 2 represents, because the discoveries are honestly only half the story. This is a spacecraft that took the harder, longer route on purpose, visited every single giant planet in our solar system, and still ended up being the one that filled the exact scientific gap its more famous twin couldn't. During its flyby of Uranus in January of 1986, it discovered 10 previously unknown moons and 2 new rings, and measured a magnetic field so strangely offset from the planet's own rotation that scientists are still working out why. During its Neptune flyby in August of 1989, the final planetary encounter of the entire mission, it discovered 6 new moons, and measured wind speeds of over 2,400 kilometers an hour, the fastest ever recorded anywhere in our solar system. It also gave us our first real look at Neptune's largest moon, Triton, capturing active geysers, shooting material miles into its thin atmosphere, and revealing that Triton almost certainly didn't form there at all, but was captured by Neptune's gravity from somewhere else entirely. This is a spacecraft that quietly built one of the most extraordinary resumes in the history of space exploration, while its twin got most of the headlines. And now, in the middle of 2026, Voyager 2 is at the center of the most important engineering attempt in the entire mission's history. Both spacecraft are running out of power. The radioisotope generators that keep them alive lose about 4 watts of output every single year, as the plutonium powering them slowly decays, a process nobody can stop or slow down. NASA's engineers have already had to shut down instruments one at a time on both spacecraft just to stretch the mission a little further. But this year, they're trying something they've genuinely never attempted before, a procedure they've nicknamed the Big Bang. And here's what it actually involves, more precisely than most coverage explains it. It isn't simply about squeezing extra electricity out of the spacecraft in some general sense. It's specifically about heat. Both spacecraft rely on internal heaters to keep their thruster fuel lines from freezing solid in the brutal cold of interstellar space. The Big Bang plan is to shut off some of those higher power heaters and switch on a different set of lower power alternatives that can do the same job for less energy, freeing up just enough margin to keep gathering science data a little longer. The reason it's called the Big Bang isn't for anything dramatic in the explosive sense. It comes from the fact that every part of this reconfiguration has to happen all at once, simultaneously, rather than one careful step at a time. Normally, engineers would test a change, confirm it worked, and then move to the next one. But at this distance, in the middle of a shift like this, there are unstable in-between moments where the spacecraft is neither in its old configuration nor its new one. And those unstable moments can trigger automatic fault protection systems built into the spacecraft, safety mechanisms that will start shutting things down on their own if they sense something is wrong. Making every change at once is meant to get through that dangerous in-between state as quickly as possible, rather than lingering in it. Tests on Voyager 2 are running through May and June of 2026 because it currently has slightly more power margin than Voyager 1, and it's a little closer to Earth, which makes it the safer spacecraft to try this on first. If those tests go well, the exact same procedure will be attempted on Voyager 1 no earlier than July, and if that succeeds too, there's a real chance an instrument shut down back in April could actually be switched back on. Here's what makes this genuinely nerve-wracking if you actually think about the logistics. Voyager 2 currently sits more than 13 billion miles from Earth. A radio signal, moving at the fastest speed anything in the universe can travel, takes over 16 hours just to reach it. Then another 16 hours for any response to come back. Every single command in this procedure, every test, every adjustment, has to cross that gap. And there's no way to pause halfway through and check how things are going in real time. This is a team of engineers committing to a fully coordinated, all-at-once change on a nearly 50-year-old spacecraft, using hardware and knowledge that in some cases predates the careers of the very people running the mission today, with a single shot, no backup plan, and no way to undo it if something goes wrong. Think about everything that's actually riding on this. Voyager 2 isn't just some historical curiosity out there drifting through the dark. Right now, it's one of only 2 functioning instruments humanity has ever placed in interstellar space, and it's the one that's still measuring plasma directly. The one that gave scientists their first real confirmation of what the space between stars actually feels like, instead of just theorizing about it from a distance. If this procedure fails, the mission loses margin it can't get back. If it succeeds, it buys more time for measurements no other spacecraft on Earth is currently capable of making, and it opens the door for the exact same fix to be attempted on Voyager 1 in July, potentially bringing a lost instrument back online. So here's what I want to know from you. Out of everything in this story, the 40-year gap created by a single broken instrument, the fact that scientists still don't fully understand why the 2 boundary crossings happened at almost the same distance, or the fact that NASA is about to bet years of extra data on a procedure that only gets 1 attempt, which part actually surprised you the most? Drop that in the comments, because I read every single one of them, and I want to know what stuck with you. And if you think this story deserves way more attention than it's getting, do me a favor and share it with someone who genuinely find this as fascinating as you do, because most people have never even heard Voyager 2's side of this story. Subscribe if you haven't already, because we're going to be covering the results of the Big Bang test the moment NASA confirms them, along with what happens when Voyager 1 gets its turn in July. Thanks for watching The Space Frontier, and I'll see you in the next one.